Good afternoon, everyone. Okay. Good afternoon, everyone. My name is Mir Zahir Abbas. I am the Operations Manager of CySecK. Welcome to today's webinar. The regular ground rules: all attendees to the webinar will be on mute by default. We will have a Q&A at the end of the presentation. You can type your question on the chat window and it will be responded after the completion of the presentation. We are also going to record this webinar and the recording will be uploaded on the CySecK YouTube channel so that you can always refer back to the video later if necessary. This webinar is part of a weekly series titled Samgacchadhwam, May We All Progress Together. The objective is to cover different topics of security over the course of this series. We want to provide a conceptual overview in these webinars to the various aspects of security and hope this will kindle your interest to explore further. This is the 12th webinar in this series. The topic of today's webinar is placement new attacks, function-based attacks, and graph HMAC. We have another interesting webinar next week on security at the hardware level. This will be by Professor Rajshekhar from IIT Dharwad. We will open the registration for this webinar shortly. We have more webinars lined up over the next few weeks, and I hope you will find this series of webinars useful. Do let us know if you have any feedbacks as well as any ideas to share with us. As usual, we will have an assessment made available at the end of the webinar. Those who successfully complete the assessment will be provided a certificate. The assessment will be kept open for 60 minutes after the completion of the webinar. The questions are from the topic covered during the webinar, so you should not have too much difficulty in cracking this assessment. Those who get 8 or more correct answer out of 15 questions will be provided the certificate. At the end of the assessment, you will also be asked to provide feedback on the webinar. Please provide your genuine feedback and rest assured the feedback will not have a bearing on the assessment. You need to have a Gmail ID to take this assessment. The certificate will be emailed to the Gmail ID you would have used to log in to the assessment in the next few days. Please make sure you provide your details accurately when taking the assessment, because the certificate will be generated based on the details provided by you. The link for the assessment will be shared at the end of the webinar. Also note that the assessment is open to only those who have participated in the webinar. Let me now introduce the speaker for today's webinar. It is great to have Dr. Ashish Kundu again with us today. Dr. Kundu took a webinar 2 weeks ago on blockchain and the Vedas connection. He is a distinguished scientist, a leader in the area of security, privacy, compliance, and AI ethics, and a distinguished speaker. He has led security and compliance of self-driving cars, teleoperated driving, and UAVs across all the stacks. He has also led the security and compliance of cloud-based healthcare and a cloud-based AI-driven education platforms. Prior to Siphons, Dr. Kundu worked as a master inventor and research staff at IBM T.J. Watson Research Center. His research has led to more than 150 patents filed, with more than 110 patents granted and more than 40 research papers. Dr. Kundu received his PhD in cybersecurity from Purdue University. His work has been recognized with several awards and honors. Dr. Kundu has been honored with prestigious Master Inventor recognition multiple times by IBM Research, New York. He has been privileged to be recognized as an ACM Distinguished Member, and in past he has been named as an ACM Distinguished Speaker. Dr. Kundu's doctoral research at Purdue University received the prestigious Sirius Diamond Award for his outstanding contribution to cybersecurity. Now I will hand over to Dr. Kundu to take you through the next part of the webinar. Over to you, Dr. Kundu. Hello.
Hello. Hi. Hello, everyone. Good afternoon again. So, thank you so much, Abbas, for the generous introduction and for inviting me here. Thanks a lot to Karthik and Abbas from the CySecK and the Cybersecurity Center of Excellence by Government of Karnataka. Really appreciate the privilege here. So
Ashish, can you run this
here
slideshow? Can you run the slideshow?
Yes, yeah, exactly, yeah. So I'm actually getting. Can you give me? I apologize. I need a couple of maybe a couple of seconds to just put it in a different window here. So give me a second. So as I'm putting the slides on, so today's talk there are essentially 3 mini talks we have. The mini talks are about the mini talks would be primarily about one is about the foundational trust that we have of functions, essentially function-based attacks. The other one will have about the placement new attacks on C++. Okay, and one more idea that we'll talk about is how do you protect data essentially about graphs. Now, there seem to be very different or disconnected set of topics, right? But in a way they are connected, in a sense of what they call as holistic cybersecurity. Okay, give me a second as I am struggling with actually sharing the Google Meet here with the Google slides here. So my apologies for that. A second here. So we'll start with talking about trust, foundational trust in programs. Last time we talked about blockchain, and in blockchain we looked at the challenge of the trust and notion of decentralized trust there. Today we'll start with, again, we'll try to continue that focus or connect that, and then start with the notion of trust in a way that software programs have a trust built into themselves, right? And the way software programs are enabled with trust are the as the following, right? We'll come back to that. Now let me see. I think I'm quite ready here to be able to share. So my apologies again. Let me do that. Okay, so that software program trust leads to memory leaks. Okay, and the memory leaks issue um, will be the what we'll be looking at on how sensitive data can be stolen by attackers. You know, that's called data exploitation attacks. Okay, now the functions can steal data from or sensitive data from stacks and heap memory. That we'll talk about there. Okay. However, in the however, the problem with I'm sorry, something is wrong here. My browser just crashed, and I'm trying to fix that.
Ashish,
Yeah, I'm trying to share the slides with you so that you can present. You can on my behalf. But I'll take care of. Let me a second here. Okay, I'm back actually. So let me my thing is started here. Okay, the browser started working. Are you able to see my screen? Abbas, can you see my screen? Hello. Hi, Karthik. Can you see my screen?
I can see your screen, Ashish.
Okay, thank you so much.
Okay,
Okay,
fine. Thanks. Bye.
my apologies. But so we are now back to presentation mode. Okay. All right. So I was talking about three talks, right? So what we'll started off trust, right? And this is where we'll talk about the trust between in a software program, okay? Which is not that much explored in the security context. And then we'll go into language, like a language based, that trust leads to certain constructs in the language, and then we'll go into data, right? And how data is going to be protected. Essentially, when you see most of the security attacks are around the crown jewel called data. People want to steal data or get access to data or modify data unauthorized manner or actually do something with the data, right? If you don't have data in a system, or if the attacker doesn't have any goal of accessing the data, then perhaps the attacker motivation would be low, or maybe something else, in order to maybe something like related to just to show off that they can break into a system. Okay, but most of the time the primary goal is to get to the data, right? That is why we have put it in this manner of trust, language, and data. So even though the talk says placement new attacks, then function-based attacks, and then graph-based graph HMAC, right? We'll start with the function-based attacks, right? I will go into, first we talked about untrusted functions, the security model there. Then we're going to placement new attacks. Then we're going to graph data. Right? Now let's start with the first one. Right? The foundational trust in software systems is that functions in a thread trust each other. So a thread, everyone knows for us what is a thread in an operating system context, right? A thread is a unit of computing which is different than the unit of computing which is a process, right? there could be multiple threads in a process, right? And the thread is a lightweight unit of computing where there is the context switch overhead is minimized, right? If you have done operating system courses, right, in a process there is a context switch overhead, but among threads you can actually do multi-threading programs to achieve a lot of functionality. Now, to look at security in a process context, there is a lot of isolation from one memory isolation between one process to the other. Okay. However, in a thread, it is well known, or in given any program which doesn't take care of any threads or processes, it is single threaded, okay, or single process, right? So, given such systems, right, functions trust each other, right? What that means that functions can access memory of each other. So if you have written a program, okay, then you can actually show that given a function f1 that you have written in code, right, and you have a function f2, f1 is called, right, and after that f2 is invoked, right, either sequentially or via other means, right. As you call such functions, right, that will be then you can actually F2 can access the data of F1 on the stack. I will show you how it will be, right? And that is a trust factor, right? So whenever you write a program, you trust that the underlying system is going to allow you to do that, right? And the functions trust among each other that is how it's going to work. If it is not going to work, then there is a problem, because then functions cannot operate properly, and therefore they cannot. There has to be some form of like inter-function communication model, okay, which is not there today. There has been some work related to function as a service, which is very similar to very much related to serverless computing or RESTful APIs. They are related, not exactly the same connection, right? Imagine there are untrusted functions. What happens? Right? You have a family of trusted people, right? You share your wallets and you share your everything with each other. However, there is an untrusted function that is come in. Okay, what will happen if they will start trusting each other, and they will also trust this untrusted function, and the untrusted function has access to the wallets. Untrusted person has access to the wallets, right? Similarly, the untrusted function here will be trusted by the sensitive function. Sensitive, what are the examples of sensitive functions? Sensitive functions are the ones which handle sensitive data or sensitive computing. Okay. In this paper, we primarily focus on sensitive data, right? However, the paper can be extended to sensitive computing in a different way, and that is where they will be going into the world of program obfuscation, okay, where you don't want to expose what kind of computing is being carried out, okay, or encrypted programs, okay. So that's a different set of world altogether to discuss, right? Perhaps we can discuss that later. But here we are talking about data that is accessible or managed by a function, right? Now, where does the data reside for a function? They reside on its stack frame and in the heap. Now, so untrusted functions can access sensitive data on stack and heap of sensitive functions. You would be asking the question, what do you mean by untrusted function? Give me an example of an untrusted function, right? So if you remember, by the way, I forgot to mention, this is a work, this is a joint work with my ex-colleagues from IBM Research. It is the paper is called Stack Vault: Protection from Untrusted Functions. Okay, and it actually has been a work by several people involved here. I actually started the idea, and then we together went on working on it for a good amount of time building the system. So Stack Vault is trying to address how we can protect the data on stack and the data that is or the memory containing sensitive data pointed to from the stack. Okay, so if stack and then from the stack data that is pointed to from, right. So the colleagues that we have, ex-colleagues who are also joint collaborators here are Chi Zhang, Zaira Sura, Gang Su, Arun Iyengar, and Ling Liu. Ling Liu is a professor at Georgia Tech. This now I'm going to skip this slide here. Okay, this one. Okay, the one here we're talking about is the function stack, right? Now, how do you invoke functions? Functions are invoked primarily in two ways, right? If you look at two functions, right, F1 and F2, either they are invoked in a sequential manner or they are invoked in a nested manner, right? So sequential manner means, let's say first function F1 invokes has a definition and has two types of data on it: password and character and key. Okay, so there is a password which is a 128-bit array or 128-byte array, and then there is a key which is a 256-byte key, right, array for the key. Right? Just to give an example, right? Now F2 is invoked right after that, right? So they are sequential. In sequential invocation, there could also be functions invoked in between. Okay, so F1 is invoked, then certain other functions are invoked, and then F2 is invoked. So essentially, the execution order of F1, F2 is sequential. Okay, what that means is that if you look at the right hand side here, right, the function stack. So you know the function stack, right? That actually grows downwards. And you start from the top of the memory, okay, and as the address increases, right, the stack grows accordingly. Right? So I hope people who have had a lot of systems related programming experience, they would understand it very well, how the stack grows. Right. So essentially, when F1 is invoked first, then the stack frame of F1 is stored at certain address, let's say X. Okay. When F2 is invoked, its stack frame will start at address Y. How and Y, since stack grows from top to bottom, the address of Y is greater than address of X. Okay. Now, in many scenarios, right, F1 F2 will reuse some form of some memory from F1 stack to actually optimize the memory usage there. Okay, that is one. The second one is F2 will have access to the password arrays and key arrays, password array and key array in the stack frame of F1, right? Because of the foundational requirement that we talked about, right? That functions in a thread trust each other and can access memory of each other, right? That is, untrusted functions can access sensitive data on stack and heap of sensitive functions. Right? We are just talking about stack right now, right? So F2 can access the sensitive data that is there in F1. Now, we haven't yet defined what is the untrusted function. Okay, we'll come back to that. Now, let's look at the nested invocation. Right, nested invocation here. F1's stack is there. There's a stack frame, and then there's a return address right on the top. Then there's a return address of F2, which is invoked in a nested manner. Okay, and then there is the data there, right? Now, how can F2, if F2 would like to access the stack frame of F1, okay? Many times, in a authorized manner, F2 can access F1 because there is some data that is there in F1 stack frame, right? However, from a programming point of view, it is discouraged to actually do memory allocation on a stack frame and pass it across to another function. Okay, but it is allowed. But however, the programming practice of doing that is avoided, is actually discouraged. Okay, so programmers who are really experts, they would avoid allocating memory on the stack frame and allowing that memory to be reused by another function. Okay. But it is allowed because there could be some related requirements and legitimate requirements they are there. You know? But in this case, what we'll focus on that F2 can actually do pointer arithmetic and reduce the address, kind of it will identify what is the instruction point. Sorry, it's the function base pointer, right? And then like the stack frame base, and then from there it will start working upwards, okay, and then access the data, right? In what kind of scenario it works, okay? I'm not going to spend too much of time because I have a limited time for each of them. We have 3 mini talks here, right? But this will tell you how it works, right? That the functions start acting in an unauthorized manner or untrusted manner, and then modify their a given pointer, and then working upwards to access data that could be on the sensitive functions, right? A sensitive function, we understand what is a sensitive function. How about what is an untrusted function? Untrusted functions are those that are perhaps are developed by unauthorized persons, malicious persons, or people you don't know. Remember, last time we talked about trusting trust in Ken Thompson Turing Award lecture. They are actually sorry, maybe there's some break of audio there, but anyway, so what I was talking about, Ken Thompson talk, he mentioned that you should think about trusting who wrote the program, right? Initially here there's a proliferation of open source code in production level code today, right? Earlier, when this trust assumption was built, that functions can trust each other, that time there is not like in 50 years back, okay, in 70s or 80s or in 90s or even early 2000s, right? Open source was not that a big deal. It is only after Stack Overflow or GitHub or programming languages like Java or Python, which actually focus primarily on using a lot of libraries, right? Only after that, the use of open source libraries or functions or copying code from GitHub and reusing that, right, became a habit in with programmers. You know, there are good and bad things about it. It helps reuse code, but it actually opens up the production level code for attackers. So imagine F2 is part of an open source library that you have brought in. Let me give an example, right? There was this data breach that was the Equifax attack, right? That affected 147 million users in especially in US, for their social security numbers, etc. And they blamed, Equifax blamed that Apache struts was the library they were using, and therefore they got broken in. Okay, we don't know whether that is a fact or not. However, if you look at OpenSSL, right, there was a malicious set of couple of instructions that allowed looking into the program memory of the server, which will then expose a lot of sensitive data like passwords or keys. Okay. Similarly, there was this recently, sometime late last year, there was a news that attackers are able to have actually released two libraries in Python, which when used can look into the .ssh directories or other directories to get sensitive keys or security keys and exfiltrate out them. Okay, exfiltrate them out, right? That is at the disk level. We are not talking on. They are not talking on memory. However, this is something we had thought about several years back. Okay, this is going to happen. So we are actually talking about a similar thing, but on the stack memory. Okay, so those F2 or the untrusted functions are the functions that are from untrusted libraries or untrusted code that is written by developers that you don't trust, right? Now we propose a notion called stack vault. In stack vault, what is provided is that there is so you've written a code, you've written a program, right? And then you want to protect your sensitive functions and their data from untrusted functions, right? You have to do that because you cannot live without open source libraries today, right? Otherwise, you have to build everything by yourself. So stack vault has two parts. One is a programmer side APIs and a compilation framework, and there's a runtime framework. Okay, stack vault programming APIs allow you to actually instrument the application source code. Okay, and they can be instrumented automatically. Okay, we haven't built the complete toolkit to instrument it automatically, but it can be done with not much effort. We built a prototype. That's why it is not automated. Currently, we do a manual instrumentation. So there are a set of programming Stack Vault APIs that goes with Stack Vault, and when the program is compiled with these APIs, then LLVM is used for generating the executable file which contains the Stack Vault specific instructions. Okay. Now, Stack Vault runtime, what it does is that anytime it determines there is an untrusted function invoked right after or somewhere after a trusted function, okay, or a sensitive function, and the Stack Vault programming APIs allow to do that, allow to determine what is sensitive or what is untrusted, right? What it does is that the kernel module will, at a very high level, right, will has a memory, has a protected memory, which will copy the sensitive data that is registered by these APIs, okay, from the memory, both on stack and on the heap pointed to from the stack of sensitive functions, and then store in the kernel module. Okay, and whenever the function returns, it actually, the untrusted function returns, it is going to put the data back on the stack frame of sensitive functions. Okay, we explored using encryption on the stack, but that becomes a problem because we have to have a key management mechanism that is outside of the kernel. Okay, and that adds additional complexity. We don't need encryption here at this point, right? To give an example here, this is the original code. Okay, let's say you have a password generator function here, and there's a nested invocation called lib_func. Okay, leave underscore function. This is a real code actually. This is if I remember the library we are talking about here. We are talking about kind of gRPC. I think if I remember correctly, maybe this is a gRPC code. Okay. And the version of the gRPC I don't remember. It is in our paper. Okay. If you look for Stack Vault on archive, you will find that. Okay. And if you need, I can send you information about that as well. Right. So leaf func is an untrusted function, right? And this is the original code. However, when we instrument it with our APIs, right? We instrument with annotated Stack Vault is sensitive. This function is Stack Vault sensitive, like password generator. Okay. And then we talk about this is a Stack Vault sensitive pointer, like password, and Stack Vault not sensitive, like age is not sensitive. Right? We mentioned this kind of annotations, right? This is part of that. Now what we also do is that we talk about register memory. Okay, we talk about that, and like we say that this is the memory, like memory malloc, right? On heap, it allocated a memory buffer of size alien bytes. Okay, and then return it as a pointed to by ID. Okay, and ID, remember ID is in the stack frame here because this is allocated right here. Now ID is pointing to heap, so we are doing the register memory ID and this is alien bytes. Okay, so what it says that this memory needs to be protected as well. So Stack Vault will take care of it. Register memory exception, like age exception means don't protect it. So age is not sensitive, right? So therefore here we mentioned age is not sensitive. The Stack Vault not sensitive. So age is not sensitive, and therefore we say that it is an exception. Okay. Then instead, right before the untrusted function starts, we say start protect. Okay, and right as soon as the untrusted function ends, we call it stop protect. Okay, then we do unregister stack. Now you must be asking, okay, let me pause it here. Okay, we are not going to talk about some very interesting point here. I'll leave you to read the paper and understand it. You can say leap function is written by an untrusted programmer, and they can actually invoke stop protect, right? Because stop protect means it will what it will do, it will call the kernel API and say, hey, get my sensitive data back to the memory addresses and stack frames as needed, right? As you are there. So leap function now calls stop protect. Why can it not call, right? This is exactly where comes the key innovation in this work, and there is actually a patent that is already been granted on this work. We call this as an identity of function. Okay, I haven't mentioned there here because of lack of time here. Identity of function means whenever you invoke a function, right? How would it know? How would the system or the kernel know that it is leap func being executed right now or password generator being executed right now? Okay, and that identity is a dynamic identity. Okay, we define the notion of identity using several parameters. Okay, I will not go into that. I'll just mention that it talks about the function signature, which is static. It talks about the library it comes from first. It talks about the .txt. So if you look at the binary of the code, right, when it is loaded into memory, right? What is the where does this function defined in the .txt, and it also looks at instruction pointer and few other things. Okay, so take a look at that. It's quite interesting. Okay, so which is not a new notion that has not been there. So because of the identity of the function, leap func cannot masquerade as saying that I am actually password generator. No. So if leap func calls stop protect, the kernel API, the kernel runtime will say no, you are not, you are an untrusted function, so I cannot allow you to call stop protect. Okay, and then we talk register unregistered stack. So in the beginning register stack, and then at the end run register stack. Okay. So these are some of the system calls, right? Untrusted function, start protect, stop protect, register stack, on register stack. All the system calls are there, right? Untrusted function, before untrusted function is called and after untrusted function is returns, start protect and stop protect are called respectively, as we saw, right? Before a untrusted function is called, start protect is called, and after untrusted function returns, stop protect is called. Okay. In the sensitive function, there are many system call APIs like register stack, on register stack. Then if you want to make it like, for example, sensitive function, here we call register stack all equals to true, like protect everything on the stack other than the exceptions that we talk about, right? Like register memory exception, like such as age, right? But there is sensitive fine-grained function in which we call register stack and unregistered stack, but there actually you have to specify the attributes we want to protect specifically instead of calling exception, right? Then which is where you talk about sensitive variable, not sensitive variable, write sensitive variable, write sensitive not sensitive variable, sensitive pointer, write sensitive pointer. Okay. And there are different parameters. I'm not going to that. Please read the paper and do that. So how does it perform, right? So we took a real world program, gRPC, which is used a lot. Okay. And we looked at the execution time. Okay. So blue here is without stack vault, and orange here the stack vault time, right? Okay. Like these are function invocations. Okay. So the overhead is essentially 0.06 time for gRPC, 1.9% is for XML stream, file upload is 1.2%, is around maximum is 2.4% for HTML tidy. So it's around 2% increase in the execution cost. Okay, which is not much at all, right? Given the security you are gaining. Now this is extremely important for how you do server programming. Normalized overhead breakdown, like context switch versus stack vault system call, because every time we make a system call, right, for stack vault, there is a context switch overhead, and that is why you wanted to also take a look at and how it matches, right? So stack vault system calls are the orange ones, and context switch takes more time actually, right? Only when a HTML tidy stack vault system call takes more time than context switch. Okay. The paper explains them more. Now, if you look at normalized compilation time comparison, how much time it takes to compile, with so runtime is like 2.4% maximum in these programs, right? But for compilation, it takes a little more time. By basically, it takes like sometimes it takes double the time because it has to compile using LLVM the system calls and other functions or other instrumented code that is added in the source code, right? So I have taken a lot of time here. I'm going to quickly go into two other talks, right? How much time do I have, Karthik?
So Ashish, if you can wrap it in the next 20-25 minutes, that will be good.
Okay, thank you so much, Karthik. Yeah, 20.
And then we can go for the Q&A.
Yeah. Sure, thank you. Yeah. So I'm sorry actually. I mean, each of this paper itself is a 1 hour talk. Okay, but I wanted to now we thought that all of us thought that we'll give you an exposure of the work all these three talks in this one talk, so that you can get what is going on and read the papers if you are interested to get more details. Okay. Now, before I go in here, I'd like to mention that most of this work here the first two work. So this one has both compilation and kernel level mechanism there, right? So systems background is necessary. This work, which is the placement new attack, okay, is more at the level of programming language, okay. If you look at the security elements I talked about, right, and we talked about untrusted functions, how to protect from them. We'll talk about placement new in C++, that is at the language level, and then we'll go into data, right, and how to protect data. That will be like crypto, okay, pure crypto, okay. But I'm not going to details of crypto. I'll just talk about the problem and talk about briefly about how the crypto works, and then we'll stop there, okay. So so the slide here is actually wrong. This one actually not currently at IBM TJ Watson Research Center. I was reusing some of the slides, and that's sorry for that. All right, this was made when I was at IBM TJ Watson Research Center. Okay. Now let's talk about buffer overflow. Here we are talking about, as it is shown, right? It was part of a talk that was given in ICDCS 2011, long time back, right? And ICDCS is a premier conference, and the paper was accepted there. So we're talking about a new class of buffer overflow attacks, which are essentially placement new attacks. Okay. So if you look at buffer overflow, I hope you know what the buffer overflow, right? You look at a buffer like in either in stack or heap. Now we understand what is the stack or heap, right? So we look at the buffer here. Allocated buffer, there's data, right? Attacker sends data which is so sorry. So the buffer overflow here is about the input data is larger in size than the allocated buffer. So it overwrote the data from 0xA100 to 0xA1F7. Okay. Now it could happen. It could occur at stack, heap, or storage. Okay. Now, what can attacker achieve? It can execute code, okay, malicious code, like such as Morris worm. If you don't know what is Morris worm, it is one of the first type of worm that was built, and is very famous, Then it can carry out denial of service attacks or DDoS attacks. It can actually turn into a bot, turn your process or system into a bot, and then control it from there. It can access sensitive information, right? So, and how do you overflow a buffer? You can overflow using string copy, mem copy, scanf, etc. All these are essentially are vulnerable system calls, right? Now, before attack, right? In a buffer overflow, before attack, you can see allocated buffer. There's a password, and after attack, the attacker has overwritten what is the password is PWD123. Okay, basically, so if the password is going to be stored in the backend, right? Then the password of the user has been overwritten as PWD123. So the attacker now can gain access to the user's service, right? So then it can carry out malicious code. However, and there is a lot of work that is already done. What is new we are talking about here, right? We are talking about a new mechanism of buffer overflow. Not only just buffer overflow, there is a whole suite of attacks that are being carried out, and we can demonstrate that. Now, the new thing is using placement new. Okay, the attacker using placement new vulnerability can carry out object overflow, which is a new concept we propose in a way, as far as we know. Stack Overflow was there. We can take care of that. Heap data BSS overflow. We can actually override stack guard in many cases. Okay, stack guard, if you know, allows some protection against stack overflow. Okay. However, I wrote code that can actually override stack guard. Stack guard is there, but still a stack overflow can be carried out. Okay, without using without even overwriting stack guard and triggering stack guard. Okay, so you can override stack guard in some cases when the attacker is a smart one. Okay, so I saw that could be done. We can also carry out code injection, arc injection, modification of values, variable pointer subterfuge, function pointer subterfuge, virtual pointer subterfuge, memory leakage, information leakage, DOS attack. Okay. One of the key aspects here is that we can actually carry out memory alignment attack. Okay. So what we can do is that you can actually push data into the memory in a way that there's an alignment requirement, right, in runtime, right, that the integers have to start at this address at certain things, or certain types of values have certain type of alignment requirement, right? You can start say, let's say, an integer at a different alignment. Okay, and by doing that, you're actually leading the system to think that there is a different value. Okay, and that will lead to the program to crash or behave in an undefined manner. Okay, so there is a denial service attack can be carried out. Now, what is placement new, right? A placement new allows you to construct or place an object or an array or a variable starting at a programmer chosen memory address. As simple as that. C++ defines this placement new construct as a standard library requirement. It is similar to new, but it allows you to place an object or an array or a variable at an address that the programmer selects. Okay. Now, it doesn't do bounce check or anything. So to give an example, like you do employee amp new employee with the normal new. So in placement new, you do employee amp new, provide the address employee. Okay. Now, if the address is allocated to the process, it will this code will run. If the address is not allocated to that process, then the code will do a segmentation fault or a core dump and then exit. Okay, that's expected. So if the address is allocated to the process, you can do a lot of things, right? It's a any non-null address, right? The use of placement new is for better memory management, safety critical applications, efficiency, and hardware level programming. I will not go into any of that. Okay. Here let me quickly show you the security issues of placement new. Any address can be used to place an object. No bounds checking, no type checking, right? There's no type checking that says, okay, only this at this address, this kind of variables, this type of variables can be allocated. No, there is no type checking. Memory deallocation of placement new is not trivial. Alignment issues, like int in place of character can be added. Okay. So overflow via placement new can be carried out. I'll quickly take into external overflow and as internal overflow. Okay. I'll encourage you to read this paper called A New Class of Buffer Overflow Attacks and appeared in ICDCS 11. This is a joint work with my PhD advisor Elisa Battino from Purdue University. And there are few talks I've given on this topic, so you'll be able to find that out. So I'll not go into details here, but object overflow is something new. I'll talk about that now. Construct a larger object replacing another object. That means you have a smaller object, and so the memory allocated to the smaller object, let's say 16 bytes, and you say I'm going to construct a larger object like 32 bytes, but it will start at an address that is the address of that object. Okay, so it will going to overwrite the 16 bytes following the previous object. Right? Construct an object from a user supplied object, where user supplied object can be larger or smaller. If it is smaller, it can lead to memory leaks. Constraint object from user supplied values. If the user has supplied values, then they are all tainted, right? So therefore, you can carry out attacks on them. Right? Now, object overflow. So these are all details. I'm not going to go into that right now. Just to give an example here, subclasses. How you can use subclasses to carry out object overflow, right? So you have an object called employee, okay, and you have an inherited class called rEmployee, okay, and which has an additional variable called bonus ID, which is 16 bytes. Okay, so this is what it shows. Now you want to we have created an employee object emp. Now you create an rEmployee object called regular employee rg employee emp. This is what you see. There is data from 14224 here, and bonus ID overrides the data. Right? So you carried out an object overflow here, right? Okay, so this is how the you can actually override. You can carry out by copy constructor. You can carry out overflow here using user supplied objects. And then you can carry a variable pointer subterfuge because you can override the VPTR. Then you can modify function pointers. You can modify the address of the pointers here. You can modify the other pointer that is already there in the object. Okay, I'm not mentioning it here. In fact, if you have an object 2, you can modify the VPTR here. Okay, memory leakage, right? So if you are constructing a smaller buffer, okay, in place of a larger buffer, you are leaking the remaining memory there if you are not reallocating it properly. Okay. So information leakage can also be carried out. That is demonstrated. So how do you address this vulnerability? You have to do bounce checking. Okay. So bounce checking on placement new is non-trivial because of alias analysis. Okay. You have to have a new library that has the Stargardt-like solution. The good thing is that GCC actually got hold of our paper. We did not contact them, but they got hold of our paper and they released a patch based on our work, and they provided that patch to as part of GCC. Okay, so there is some placement new protections now after this work was done. Okay, and this is I don't remember exactly. Perhaps this happened in 2015 or 16. Okay, so I'm going to pause here and summarize what we have covered till now. We have covered essentially. Let me quickly go over the. Okay, we have covered the trust, like protection from untrusted functions. We have covered how placement new attacks can be carried out, and how we can. We haven't covered much of how we can protect it from, because that's a more detailed work discussion, right? We'll go into data now. How do you protect data such as graph HMAC? Okay. Now, as I said, untrusted functions that work like on Stack Vault. That was a joint work with Chi Zhang and others from IBM TJ Watson Research Center. Placement new was a joint work with Elisa Battino from Purdue University. And then the graph data structure, that is a joint work with again with when I was at IBM TJ Watson Research Center, and people from Purdue University. Okay. So the paper appeared in IEEE TKDE in 2018. It is efficient and scalable integrity verification of data and query results for graph databases. Okay, so what is a graph, right? And there is a graph is essentially, here we look at a directed acyclic graph, right? Essentially a set of vertices and edges, right? It can be an undirected graph or a directed graph. In this case, we are talking about a directed graph where each edge has a direction, right? From one vertex to the other. Right? There are graphs with cycles. There are graphs without cycles. There are graphs with one source. There are graphs with multiple sources, and there are different types of graphs. Okay, here we will cover them in a generic notion of graphs, right? Like there's a graph with cycle here. For example, there's a cycle between B, D, E, C. Okay, so that's the cycle here, and there are DAGs with multiple sources like source 1 and source 2, and this is also a kind of a disconnected graph. We can call it as a forest, right? Now, why graphs are important? Right? Graphs are important in many ways. In a way, everything is connected, right? As Einstein mentioned, right? God doesn't play dice with the universe. In that context, right? That means that nothing is random. Means there is some connection between one thing and the other. Now, the connection could be very trivial or something. He didn't mention about anything about that, but I'm just trying to extrapolate from that thing, and many people have done that, is to that things are connected, right? That's why I'm making a general statement here, is that everything is connected in a way or the other, right? Now, that while that is a philosophical statement, right? You look at today about Google Maps, right? In Google Maps, you want to go from one place to the other. How did that happen? Because they have represented the road network as a graph. Okay, so you are able to find paths from one place to the other. Right? You look at genomic graph, right? So genomic data sometimes is represented as a graph. You look at transactional data, right? Your transactional data can be represented as a graph, because one transaction to the other, one transaction between two persons is an edge, and another transaction, another person is an edge. Okay, so we have worked on fraud analytics using deep learning, etc., using graphs. That could be a different discussion later, another time. Right? So graphs are very important. The graph data, as you see, genomic data is sensitive in nature. Map data is sensitive in nature, because if I modify and say there is a path, there is a road network from India to let's say Europe, via Atlantic, right? Then like where you can have ground vehicles going, right? That will be wrong. That will not be a good thing, right? So you don't want someone to modify your data, right? So you want to graph data is being important since last several years. Neo4j database is there, and there are Tiger Graph databases there. There are several graph databases. In these graph databases, there are two types of graph data publishing and query models that are there, right? One is two-party data publishing model. There is a database graph data owner, like you have a graph data, you own a graph database, and the database client connects to it and gets query results, right? You have a third-party data publishing model where you have a graph data owner who uploads their data to a graph data service, right? Suppose you have genomic data, you are a researcher, you publish this genomic data to the graph data base as a service, and then there are database clients who are other researchers who want to query genomic data and receive them. Okay. Now, in both of these contexts, right, you want to ensure that the data that you receive has not been modified in an unauthorized manner. Right? You want to ensure that the integrity of the graph data is intact. Right? So imagine that the graph data resides in the memory here on the graph database. Okay, and by carrying out function-based attacks or by carrying out placement new attacks, the graph data has been modified, or by some other means. Okay, I'm just gave two examples in this context here to today's stuff, right? But the graph data can be modified in many ways, right? Once you modify the data, then database client they need to know the data it receives is authentic or not. or whether the data has been modified in an unauthorized manner or not, whether the data has been tampered with or not, right? So that is where comes requirement of the notion of HMAC, right? Will in this context, the database client receives, in the third-party model, the database client many times receives a query result, like which is a partial data, right? Even in two-party model also, the database client receives a part of the graph as a query result. Right? Now for verification of integrity, there are many things, right? Message authentication codes, HMAC. There are also digital signatures, right? We have worked on. I personally worked on digital signatures. Leakage-free reductible digital signatures is something I defined and developed during my PhD and later are for graphs, right? However, they are expensive because they rely on public key cryptography. Okay. It is known that the digital signatures for even bit strings, like bit strings, they support several security capabilities, like authenticity, owner authentication, because by using public key certificates. Then you have non-repudiation. Non-repudiation means then that a given signer cannot claim that he or she did not sign that specific message, right? And there are several other security requirements. In many scenarios, all those security requirements are not needed. What is needed is to just verify whether the data has not been modified, okay, in an unauthorized manner. So that is where comes the notion of message authentication code. Okay, hash. That is where comes hash, but hash doesn't. Hash can be modified very easily, right? Suppose you modified the data, and you can replace the hash with with the hash of the modified data, right? So message authentication code protects from that, right? Hash is very fast. Right? Message authentication is very fast. Is a hash of a key and M. M is a secret. K is a secret key, as a kind of a symmetric key shared with the client earlier. And so you take hash of key and the message concatenated together. That becomes your authentication tag, and that is message authentication code, right? However, there are some attacks on HMAC, and therefore the hash-based message authentication code was developed. It was Hugo Krajcik, who was my ex-colleague at IBM PJ Watson Research Center. He developed that algorithm, and it became HMAC is used everywhere for bit strings. Bit strings are used. Bit strings are like 0101 whatever, right? And you share them either fully or not share them at all. So if you ask for a bit string, the bit string is given to you, fully. Okay, like a message, an email. An email is either given to you fully or not given to you fully. Not given to you at all, right? In many times there could be scenarios where you give the part of the email, but that's a different context, right? So in a network, either you get a message, a network packet fully or not at all, right? That is where MAX and HMAX work beautifully. However, in a graph, because graph is a semi-structured data, you share them partially many times. You don't share the whole graph many times. You say, oh, this is part of the graph. This is a subgraph. Take it, right? So in that context, can you apply existing HMAC techniques? No, you cannot apply, because if you take a graph and serialize it into a set of bits, then you have to share the graph as it is to the other user. Now there is also a challenge or issue of how do you or programmatic problem that how do you serialize a graph? If you don't serialize it in the way it was the HMAC was created, you will not get the you will not be able to verify the integrity of the graph, right? So therefore, we developed all those techniques in the context of graph HMAC. This is the first foundational paper in that area, there are two types of HMACs. One is for a two-party model where you share the full graph. One is a GHMAC and GVerify. Okay, and then the other one is reductible HMAC, where you share part of the graphs, right? That is where we have four functions: RGGen, which generates a key; RGHMAC, which generates a reductible HMAC; RGReduct, which reducts the graph and generates an reductible HMAC for the reductive graph; and then RGVerify, which verifies the reducted graph with the reducted HMAC. Okay, all the crypto related algorithms are they are in the paper. Please take a look at them. I'm not going to go into that. But there also a notion of fail one, fail stop HMACs for graphs, which is a new concept. So for bit strings, right, either you receive the full data or don't receive the full data, right? And when you try to do a hash, you hash the whole data. But in case of graphs, we actually do a traversal. We do a depth first traversal. While you compute HMAC, we do a depth first traversal on the graphs. Okay, and as we do the traversal, we do some form of computation of some of the hash values. Now, whenever we see that a hash value doesn't match with some of the values that are out there, right? Then we can actually warn the user that the HMAC is not going to match for this graph. Okay, without traversing the full graph that is received, right? So then you give a warning, but continue compute the HMAC, right? So that you can determine what are the other vertices that do, or edges that do not match with the HMAC that is received, right? But fail stop will stop right then and there. And these things are very important in terms of how you do recovery from errors, okay, or a stop, and you don't spend more time in computing HMAC that is not going to, or verifying HMAC that is not going to be validating the graph that you have received, right? So those are new concepts we have added. We took several data sets, like we took, for example, two data with edges like 17 million edges, that is really huge. And for that, we carried out experiments. Our performance was really good for all of them. Now, how we implement this HMAC? I'm sorry, I would have loved to go into all those details, but I don't have enough time to do that. Just to give an example of how we implement HMAC for graphs is that we take a graph, okay, we have generated a key, or the key has been generated already using RGGen. We take the graph, we determine what are the sources, okay, of the graph in a way, and then we traverse the graph in a depth first manner, okay, and then we compute the hashes bottom up. So we hash the graph in a way that can be recomputed by the receiver, and then we compute the HMAC around it, right? Now, for reductible HMAC, it becomes a more complex process. Okay. All right. So let me pause here. I think those are the three different topics we talked about here. Okay, I'm going to quickly show you what we talked about today. Again, right? We talked about trust in the sense of untrusted functions. We talked about placement new attacks, and we talked about graph HMAC, right? So the summary is that function-based attacks are carried out by untrusted functions, some sensitive functions, and we have developed a system called Stack Vault to protect from such attacks. Okay. However, Stack Vault doesn't protect from all attacks that can be carried out by untrusted functions. Okay. It only protects the data that is managed or stored by sensitive functions on the stack and the heap address and the memory that is pointed to from the stack. Okay. now there are certain notions of undecidability around alias analysis and trying to determine what addresses can be accessed by other addresses, and therefore it is stack vault doesn't solve all those problems. It is impossible to solve all those problems, okay, because of the hardness. However, there are many other problems that need to be solved, and this is a new form of attack called function-based attack, or untrusted functions and their attacks. Placement new attacks, again a new form of attack. We discovered this vulnerability as I was working on a kernel OS, and then a kernel and of a storage OS, and then found that placement new is used there, and perhaps can be vulnerable, and from there I started working on this topic. Okay. And then we developed the concept of graph HMAC. We have worked on graph digital signatures, leakage free reductible signatures, and leakage free sanitizable signatures, and digital signatures for graphs earlier, and graph hashing earlier, and that led us to work on graph HMAC for making it more efficient and used for graph databases. Okay, and that is how these are the different talks focusing on trust, language, and data. Thank you so much for listening to me. Please send your questions, shoot your questions. And I apologize for the delay in the beginning. And
thanks, Ashish. I think
sorry
it was
for that.
a really good session. Hello.
Hello. Yes.
It was a very good session now. Okay, and I have posted some of the questions in the WhatsApp group. There are some 6 questions. Can you answer them?
Sure. Let me. Okay. Question only. While using enum, the data present inside enum are overridden on itself for minimizing memory allocation. How to implement data protection on such kind of system? Okay. So this is where you are talking of enum in what context? Because enum is used in many languages. I hope you are talking about C++ here, right? And now for that kind of system, I would say that stack vault can help. Okay, you can use stack vault kind of mechanism. The other one is to do about if you are looking at protection of the data that can be exposed. So when you say data protection, I have to understand what do you mean. What kind of data you want to protect, or how you want to protect the data from, right? You are trying to protect the data from leakage, or you want to protect the data from overwriting, right? I think you are talking about data protection from leakage, right? In that context, you can actually clear the memory of enum that is used by enum, and then allow the overwriting of the memory there. Okay, so that is where comes like memory reset. So there are few years earlier, even kernel data was present in buffer before the memory was reallocated. But recently, Linux kernel and other kernels, and even the compilers are clearing the memory. Okay, so we can use them. Now, question 2, the untrust function. Okay, hello. In one of your code snippets, an untrusted function was executed between start protect and stop protect. Assuming that code runs on an FPGA and an attacker has access to that, when the attacker tries to introduce a glitch in the supply voltage of the hardware and start protect function is about to execute, the basic tendency of this glitch is to skip start protect line and execute untrusted function. Can stack vault protect against such an attack? Okay, this is an excellent point, and I love it. Okay, thank you for asking this question. Now, this is this is where comes assumption when you build a system, right? So we did not assume that the attacker has access to the hardware supply voltage. Okay, if an attacker can introduce the glitch and can actually make the hardware skip start protect function, then yes, then stack fault would not work. I agree with you, or if you are thinking, right? Because we have not designed stack vault to protect from hardware attacks like this. Okay. We assume that the attacker doesn't have access to hardware or the kernel as a privileged user. Okay, and that is a security assumption we have made. But this is a great point. Okay, perhaps more work needs to be done, and systems to be developed to protect from such attacks. Thank you for this question. So this shows that we have actually people thinking in that line. I hope people are going to write take these works and then develop it further and write more papers or especially solve problems. Not about writing papers. It's about, as you see, that what we are doing or what I am doing. I don't want to just take one work and then it's like squeezing a lemon to get every bit out of it. It's like then you build on incrementally on that work. Okay. My interest is more about identifying foundational attacks, foundational threats, and foundational defense mechanisms, and bring it to the world, and then let the researchers and others to actually think about whether it is good enough and extend it or reject it or build something around it. Okay. So, and of course there are some scenarios in which we have taken one problem and taken it forward into multiple papers, but it is the nature of the problem, or it is part of the PhD or something, right? So what I do is that we come up with an attack and then leave it to the world and see, or come up with a solution and leave it to the world how they solve it. So I hope that the esteemed listeners here and at other places will actually work on developing solutions around these attacks. That's important for our security. Right? What is reliability of HMAC with collision cores? Okay. See, the HMAC is highly evolved. Okay, and if you, as long as so HMACs are known to have collisions, especially when the attacker is aware of the symmetric key K. Okay, so if I go into the definition here, right? There are too many slides here. Okay, this is the key, right? This is the key here, right? If the attacker has access to the key, then perhaps the attacker can force a collision attack. Actually that was the primary problem with MAC, message authentication core. Now HMAC, there are some work around that area. Okay, but if you have the key K as secret, right, then it is essentially going to rely on the hardness of the hash function. Okay, so if you can break an HMAC, that means that you have broken the hash function there. Now, how is memory allocated in a graph-based database? Okay. Now that differs from one graph database to the other, right? Memory can be allocated for let's say if he is talking about like incremental graph, like you are incrementally adding vertices and edges to a graph, then you are going to allocate in that manner, right? For one memory. But if you are for page by page, right? But if it is multiple graphs, right, then it's different graphs that you are allocating memory for. Then you can perhaps look at memory as not page by page, but you can look at as a different unit. Like you can allocate a larger unit, like let's say 16 pages, and then allocate memory there. So that is, it is a very subjective question on how you implement a graph database or what kind of graph you store there. Okay. The next question is, why do we use hash instead of encryption in a digital signature? Similar kind of problem. Okay. See, this goes into the basics of why hash functions are there, why one-way hashing is there, okay, and why encryption is not used for authentication, right? I see, if you have encryption is used for protecting confidentiality, okay. If you encrypt the data set and the other user has access to the key, or
Hello, Ashish. Hello. Ashish, your voice is not audible.
hello. Yeah, sorry, I my connection dropped because of, I think there is a 1.5 hour, 90 minutes of continuous call enforced by Geo for us in India, so therefore it got dropped. So we are talking about the question 5. Why do you use hash instead of encryption in digital signature or similar kind of problem, right? So see, encryption, the way the mathematical functions work is that it allows you to decrypt data and know what the data is, right? But in digital signature or in hashing, you have access to the plain text already, right? But you want to verify whether the plain text is the one that was sent by the owner, or or has been modified after it was sent, right? So so that verification is a different problem altogether. Now, can you use encryption there? You can use encryption to protect, and say that the user only sees that. Now, can you the data can be modified in many ways, right? Data can be modified while it was being transmitted. Okay, so it was encrypted right before it was transmitted. The data can be modified, and an encrypted version of the data can be sent. So let's say the message M here, right? In the display in the slide here, message M is modified to M prime, right? Now M prime, the attacker might have access to the key. So the attacker resides in the kernel memory, okay, or the attacker resides in the network library, which has access to the kernel memory, right? So attacker can actually modify this message to M prime and use the encryption function to and the key that is already there and encrypt it, right? And then send the encrypted data. So the data has been modified, right? The M can also be modified before it was encrypted by the attacker. In case of third-party models, right? In case of, let me see, in case this is what I'm talking about two-party model. In case of third-party model, the data can be modified at the service provider. You don't trust the service provider, like cloud, right? You don't trust the cloud provider in many scenarios, right? Because it has access to the hardware systems and underlying infrastructure. So you don't want the service provider to be able to modify your data. So therefore, the graph data owner will, even if it encrypts the data, the service provider has to decrypt it, unless it uses fully homomorphic encryption to carry out query processing. So the graph data owner has to sign it or create an HMAC, send it to the service provider. That the service provider does not have to get access to the key, okay, or regenerate the HMAC there, right? So therefore, that is your fundamental, that is your confidentiality and integrity or authenticity are two different problems. Okay, I'll basically encourage the person who asked this question to actually take a deep dive into those two topics and understand their problems there. We can discuss that further if you are interested in asking questions. But question 6, let's go there. Just to get some information, what are the security attacks faced in AI technologies? Oh, so security attacks faced in AI technology. So you should already know adversarial machine learning, right? The adversarial machine learning is about attacking a given machine learning model or an AI system or machine learning system where tainted or compromised input will be given, and it will classify it to be a different one than what the human eye sees. Okay, like a computing or what traditionally will be looked at, right? So, for example, you give an input of a cat with modified pixels in it. Okay, it will the machine learning model will say it is not a cat. It is a human being. Okay, kind of thing. Okay. What are the other attacks? The other attack is called data poisoning attack. Okay, where you use data in AI a lot, right? That's the key there in AI. So you use data to train and test. Now, if I have poisoned your data, right? If I have given you a data set of face recognition, but there I'll put the faces of dogs as well, okay, and then that will, and that training will happen of human faces as well as dog faces, right? So tomorrow when a dog face is given, the system will say, oh, this is a human face, okay. So that is I'm giving a very crude level of attack, data poisoning attack there. There are certain other types of attacks that are there in terms of cheating. The machine learning systems can cheat about training. Training requires a lot of memory and time, right? So machine learning systems can cheat that they have trained on all the data sets, right? So we have a paper on arXiv called Uncheatable Classification. Okay, take a look at that. There are attacks, couple of attacks I cannot talk about here. We are still writing some papers on that. But there are, like any technology, there will be vulnerabilities and attacks, right? So and AI is quite vulnerable to many different types of attacks. Okay. Now, question 7: what is placement new attacks? So placement new attacks are the attacks that are carried out by exploiting placement new vulnerability, right? So the second mini talk I talked about is where we introduced the placement new here, right? I introduced the concept of placement new, and that concept is about that you can place an object or an array or a variable starting at a programmer chosen memory address. Okay, that is placement new. Now you can actually exploit this construct and carry out buffer overflow attacks, object overflow attacks. You can carry out all these attacks I mentioned here, like 4, and there are 9, about 13, 14 different types of attacks we can carry out by exploiting placement new vulnerability in C++. Okay. To be honest, I have across the world I have interviewed maybe thousands of candidates for different positions, and I haven't seen anyone to know much of placement new. Now, is that a good thing or a bad thing? In a way, it's a good thing that people don't know what is placement new, so they will not be using it, right? Therefore, the impact of the vulnerability is very less. However, if you look at the code that is out there, like Firefox, okay, or you can look at other servers, or embedded programming, or OS programming, placement new is used a lot, okay. because of its way of memory management there, right? So memory management is highly specialized by using placement new. That kind of memory management allows a programmer to be able to decide how do they want to allocate and deallocate memory, right? So you don't rely on garbage collectors always. So in that context, the developers, if they don't know placement new, they are not also going to know what are the vulnerability that is posed by placement new. So tomorrow, when they're exposed to such a construct and use that, they'll be using it like a naive programmer, right? And they'll be opening their systems they're developing to attack. Right? That is where it is important to know when you call yourself as an expert in a programming language, you should know most of the constructs there and know the security implications of those constructs. All right. The next question is how HMAC is secure than MAC. Okay, very good point. How HMAC is secure than MAC, right? I'll leave that to you to go and read some. These are basic discussions out there, but let me give an example here. You look at message authentication code here, which is hash of a secret key between the sender and the receiver, and concatenated with the message, right? However, suppose you could guess the key. Here it is a concatenation, right? So suppose you know the first part of the key. You don't know the key first part, but you constructed a message m prime, which has a suffix as m, and the prefix has some bits which are suffix of k, right? So basically, you have taken the concatenation, and you don't know the sum of the prefix of that concatenated string, right? Now, what you can do, you can carry out a dictionary attack or a forced pre-image attack, okay? Or because you know that tag already, right? So you want to replace m with m prime and then send it across, right? Or you want to use that key but replace m with a different m, right? Okay, so there are already research that talks about sorry for the background noise there, but there are already work out there. Now, if you look at HMAC, right, what HMAC did is that it did not concatenate with M directly. It got concatenated with something some other bit strings called OPAD and IPAD. Okay, given the context, we are already into like 6:38 p.m. I'll leave it there. I'll encourage the reader to go and or the questioner to actually go and read about it. And if they have further questions, they can send me an email. I mentioned my email there, kundu@acm.org. Okay, and talk about that. Now there is a question 9. By using buffer overflow attack, can we log into any systems like hacking? No. Again, so you cannot log into any systems by using buffer overflow attack. You can log if the authentication system you are trying to break in has a buffer overflow, and you have to see whether that buffer overflow can be used to access the system, then yes, you can do that. But it is not like, okay, I can give you a hammer and you can go and break a mountain. Okay, to break a mountain, you need to know the type of the mountain and what type of hammer it is. Okay, so this is a general question, and the other point I like to encourage here is that I'm not encouraging here. I discourage people to go and break into systems. The reason why you should know what is the problem is to protect from that problem. Okay, but using buffer overflow attack of a system doesn't mean that you can log into that system always. You can carry out some attack, but if the system has been developed by expert security engineers, right, then they would ignore, even if there's a buffer overflow, they'll ignore that buffer overflow input from the attackers. Okay, this your tent analysis come into play. Okay, so those are 9 questions. Are there any other questions?
I think there are no other questions.
Okay, so if there are other questions, let me know. But thank you so much. There are some nice, interesting questions that were asked. I really enjoyed answering them. But really enjoyed talking to you guys again.
Thanks a
Today.
lot,
Thank you.
Ashish. It was an interesting session today. We'll hopefully have some more sessions in future. Okay. Thanks a lot for being part of our CySecK webinars.
Thank you so much, Abbas, and thank you so much, Karthik, for hosting me. It has been my great privilege and honor. And thank you so much for also partnering with CySecK, which is our startup and part of CySecK Hack Accelerator. And thank you so much, everyone. Have a great evening and enjoy. Stay safe and protected, please. Thank you.
Okay, thank you. Okay, for the audience, I would like to say that I have posted the assessment link in the Q&A chat window. Okay, the passing mark is 8 out of 15. You have to score 8 out of 15. Those who score 8 out of 15 will be getting the certificate. And the link will be accessible for another hour. Now it's 6:40. The link will be made available till 7:40. Post that, the link will not be available. And the other thing which I want to mention is